Welcome to lecture number 23 for ECE 461 Control Systems, Lead Compensators, Design using Root Locus. Now, as a little bit of introduction, the goal in compensator design, that's given a plant and a feedback system, how do you specify the compensator that gives you a good system, good tracking, and a quick response? Good tracking and a quick response means make K of S as large as possible. High gains give you better error constants, smaller errors. High gains give you a quicker response. Again, it's like when the light turns green at the stoplight, you floor it very quickly, gives you quick response. But I have a constraint. I don't want to make the overshoot too large. So how do I specify K of S so that the gain is as large as possible, but not too large? The approach that we've been doing is using root locus. When I have the plant, I draw the root locus plot, and then if I want 20% overshoot, I draw the damping line. The point on the root locus plot that hits the damping line is the highest gain possible that doesn't meet, violate those constraints. Now, if all you have is just gain compensation, I'm stuck on this one-dimensional curve. I can't make it go any faster. If I could add dynamics, say add a 0 and add a pole for the compensator, that would pull the root locus left. By pulling it left, I would speed up the system. And to kind of illustrate that, here I've got a fifth order system heat equation, same one we used last time. I've got 5 poles, modeling it. To illustrate the poles and zeros, notice that poles repel, zeros attract. So if I add a pole, and I look at this part of the root locus, that's your dominant pole. As I move the pole that I added around, the pole repels it and pushes it further right. So poles are bad. They destabilize the system. In contrast, zeros are good. What a 0 does is the 0 attracts the root locus. Notice it pulled it left a little bit. As I bring the 0 to the right, the 0 looks like a plus charge. It attracts the root locus, attracts the electrons. As the plus charge gets over here, I'm pulling the root locus left. That's the purpose of the 0. That's the idea behind a lead compensator. I want to pull the root locus left as far as I can. The challenge, though, is where does 0 go? In addition, if I add a 0, I have to add a pole. 0 is a differentiator. A differentiation without anything else just causes noise. So if I add a 0, say I want to put a 0 here, I really also have to add a pole. And typically what you do is put the 0 to the right to cancel the pole. Put the pole out of harm's way, like 3 to 10 times further left. This pole is bad. It is repelling the root locus, but stick it 3 to 10 times further out, and the effect on this part of the root locus isn't that large. It's too far away. And that's the idea behind a lead compensator. I'm going to add a 0. The 0 pulls the root locus left, and then unfortunately I have to add a pole. Put the pole out of harm's way, say 3 to 10 times further left. The first question we need to answer is, if I add a lead compensator, which pole do I want to get rid of? So again, let's look at a fifth order system. This is the fifth order heat equation that we looked at before. I've got 5 poles I can get rid of. Which one do I want to toss out? And again, kind of see from RL tool, let's get rid of the pole. I've got a 0 I can move around, this guy. If I cancel, put the 0 really far left and basically haven't done anything. If I bring the 0 in and cancel the fast pole, now comparing the two, there's not a whole lot of difference. This is so far away from the dominant part of the root locus that it has almost no effect. So canceling the fast pole is the wrong idea. Instead, what I want to do is cancel one of these poles. And the question is, which one do I want to get rid of? The slowest pole, this one right here, which looks good, it brings the root locus really far left. Or do I want to cancel the next slowest pole? And I've seen textbooks that argue both ways. Personally, I would say you cancel this pole right here. The reason being is I like type 1 systems. If I had a pole at the origin, I'd want to keep it. That gives you better tracking. This pole isn't at the origin, but it's close. What that does is that makes the gain high at DC, gives you good tracking. If I get rid of it, if I can get that pole, there's 0. If I get rid of that pole, say put 0 right on top of it, now this is the closest pole to the origin. I'm going to have lousy tracking. Faster system, but lousy tracking. In contrast, I can't pull it anymore. Let's erase that 0, add it back. In contrast, if I got rid of this pull, not the slowest pull, but the next slowest pull, and here I didn't get exactly right. I have pulled the root locus left. Again, comparing it, you'll look at this part of the root locus. If the 0 is way over here, the dominant part's right around -1. As I bring the 0 left, I'm pulling the root locus left. And that did speed up the system. So, deciding which pull to cancel. Again, your first option would be, given a system, let's just start out with the gain compensation. What's the system look like with just a gain compensator? I would draw the root locus, find out where the root locus passes through my damping line, find out that's right around 0.69 plus j 1.3, find k. K is 5.5. So that's my result. I've got a type 0 system, kp is 3.4. That's the DC gain of g times k. The real part's 0.69. 4 of the real parts are settling time. That's what I'm starting with. Can I do better? Well, if I add a lead compensator, I've got to cancel one of the pulls. So let's cancel the fastest pull. What that did is that took the root locus, the blue line, and pulled it left just a little bit, not a whole lot. Which again is what we saw before. Canceling the fast pull does squat, so that's not the pull you want to get rid of. Second option, if canceling the fastest pull is bad, let's cancel the slowest pull. That looks like that would be good. I'd put a 0 right on top of that pull, add it 10 times further out, just because 10 is kind of a nice number. And what it looks like is I've taken this pull, it looks like I've slid it to the left from 0.32 to -3.2. What that does is takes the original root locus, this line, and pulls it left. I now have a faster system. That's good. That's what a lead compensator is supposed to do. What's bad is that I've made the error constant much, much worse. It's about 3 times worse. The reason being is I used to have a high gain at DC due to this pull. That's close to s equals 0. It's no longer there. Now that's the closest pull to s equals 0. The DC gain isn't quite as high. If this pull was right at DC, I'd have a type 1 system and have no error for step input. So getting rid of that pull is actually bad. Get a quick system, but bad tracking. In contrast, if I kept the pull at 0.32 and instead look at the next lowest pull, the pull at 2.018, get rid of that one. Now what happens is I took this pull, moved it left. Now the pulls between 0.32 and 5.4, this one and the one over here at -5.4, come together, split apart, and form this root locus. I've moved the system left. That's good. I've kept the pull close to s equals 0, so I'll still have good tracking. And I'll have quicker settling time. The real part's gone left. And that's what you see in this case. If I cancel the slowest pull, or next slowest pull, find k of s, find the spot on the root locus where the angles add up. Once I find it, find k, and then you get the settling time. And I'd like to show you kind of a nice way to do this. The way I'm getting all these decimal places is I'm using a numerical solution to find k. If I know k of s, well, let's just do it this way. I'm going to take g of s, and I'm going to cancel this pull, this one right here, and move it 10 times further out. So that's g times k. Let's make that gk. I now want to find out what point on the root locus is on this damping line. So what I'm going to do is I'm going to guess. Search along this line till the angles add up to 180 degrees. When they do, that's my spot on the root locus. So let's just guess s is -1 plus j times 2. 20% overshoot corresponds to a 2-to-1 ratio. Now let's evaluate. And notice that it should be negative real. There's a complex part. So s is wrong. That point's not on the root locus. So let's try a new guess. Let's make s 10 times bigger. reevaluate, and that got better. The complex part got smaller. Let's try it again. Still better. Ooh, really close. Let's make it 1% bigger. And I went too far. I got a sign flip on the complex part, went from minus to plus. That means I've gone too far. So let's make it a little bit smaller. And it looks like right about there. And so S is minus 1.355 plus J 2.71. That's the spot on the root locus. At that point, the angle of G times K is 180 degrees. The gain's wrong though. To find K, at any point on the root locus, G times K is minus 1. So if I evaluate G of S and find K to make the gain 1, that's K, 102.94. Actually 102.59 if you carried out a few more decimal places. That's kind of a trick to find the spot on the root locus. I'm just doing in numerical techniques, searching till the angles add up to 180. Or you can draw the root locus and see where they intersect. And some computations. Once you find K, I have K of S. Once you know where the poles are, over the real part is your settling time, and Kp is just the DC gain. So it is G of S as S goes to 0 times K of S as S goes to 0. And you get 6.4. So the results, if I just have a gain compensator, I've got Kp is 3.4, 5-second settling time, cancel the slowest pole. Kp just got a lot worse, so that's the wrong one to do. Cancel the next slowest pole. I've got a better Kp, better tracking, and better speed. Basically the best of all worlds. That's what a lead compensator does for you. The initial input is at t equals 0. The output is 0, the step input is 1. So the input of the system is just K, DC gain of K. For a gain compensator, I initially apply an input of 5. That gets it moving. With a lead compensator, I apply an input of 102. That's like at a stoplight. To get your car to respond quickly, you floor it, then back off. That flooring it is what speeds it up. That flooring it is what makes the system faster. And part of the assumption you're making is that my system can tolerate an input that goes from 5 to 100. If I can do this, this lead compensator works. If I can't do that, well, maybe instead of doing a 10 to 1 ratio, I should do something more like a 2 to 1 or 3 to 1 ratio, pole to 0. That ratio kind of tells you roughly how much of a kick you're going to give it at t equals 0. So in summary, with a lead compensator design, I keep the pole near s equals 0. I pick the 0 to cancel the next lowest pole. That keeps Kp large. I then pick the pole to be 3 to 10 times larger than the 0. You stick it to the left out of harm's way. And then that's the previous design, gain compensator. Now find the gain to give you your desired overshoot. And the resulting step response, here's the original system with gain compensation in red. With the lead compensator, notice the output's closer to 1. I've got better tracking, higher DC gain, less steady state error, and I have a faster system. If I want to implement a lead compensator, there's a couple ways to do it. In hardware, what I can do is build an op-amp circuit to implement it. This is like a variable resistor. At DC, the resistance is RA plus RB. At high frequencies, like during the transient, it's just RA. So at high frequencies, like when the light turns green, the capacitor shorts out and I have a high input. Then in steady state, I back off. So this is kind of like an automatic flooring. If I give it a step input, I floor it and then back off. That speeds up the system. The way you design it is, if this is my lead compensator, I've got 3 constraints. I've got 4 degrees of freedom. What that means is somebody's arbitrary. I can pick one at random, like R2. Let's make R2 1 mega ohm. Then the other 3 drop out. In the circuit, as S goes to infinity, capacitors are short, all I have RA. So as S goes to infinity, the gain is R2 over RA. S goes to infinity, the gain should be 101. So R2 over RA is 101. R raised 9.84K. At DC, the gain is R2 over RA plus RB. At DC, plug in S equals 0 and get a gain of 10. That says that RA plus RB is, 92K. Solving, RB is 88K. Now, anything I can do in hardware, I can do in software. In software, I can implement this filter by first taking this filter and making it a proper fraction. Take s plus 20.8 minus 18. S plus 20 over s plus 20 is 1. Leaves you minus 18 over s plus 20. This is a filter. I can implement that as a first order system. Create a dummy state z, and when I cross multiply, z is this times the error. Sz, right here, is 20.8 brought right minus 20.8 times z plus 18.7 times the error. Then the input B0 is just 101 times your error minus your dummy state z. And to illustrate that, in software I would implement it as follows. Here's my dummy state z. It's the filtered version of E. And the voltage, that 0.5 came into play because the extra poles added some instability, and I had to adjust the gains to get the overshoot. But here's what you're seeing. The input is snapping up and down. That's trying to get the output right here to respond more quickly. And to get it to heat up, because the heat equations don't like to respond that quickly, I need to slam the input high to get this to start warming up, then slam it low to cool it down to get it from overshoot, then we get high again. That's what you get. And again, let's run that again for you. If you watch the tip position, temperature at 10, here's your step response. It's responding more quickly. To do that, the input has to slam really high. I get my overshoot, and then comes back down. And that's a software way to implement your lead compensator. Now, if you have a lead compensator, a single lead compensator speeds up the system. That's good. Actually does two things. I get a faster system and better tracking. So if a single lead compensator is good, why not add two lead compensators? And it turns out you actually can. For example, if I have this heat equation, if I had the first lead compensator, I keep the pole at 0.32 because that makes it almost type 1. Get rid of the next pole at -2 and move it out to -20. That gives me the lead compensator system we just looked at. If that's still not fast enough, now let's take the next pole at -5.4 and push it out to -53. Gives me a faster system. And I could keep on going, keep going. In theory, I could make the system as fast as I want. If I had two lead compensators, I now have a system that is going from here to here, maybe 3 or 4 times faster. The input, however, as S goes to 0, that's the initial voltage. I'll be applying 1,700 volts rather than 5 volts that I have with gain compensation. Nothing comes free. If I want to make the system faster, I need to apply larger input. That's kind of like your car. When the light turns green, you floor it. If I had a bigger engine, I could accelerate faster. There is a limit though. When the mechanical engineers designed the system, they picked out the engine, the motor, for some reason. They'll over-design it slightly, but they're probably not going to give you a factor of 100 in the over-designing. So in theory, I can make this as fast as I want. In theory, I can take a Chevette and make it go 0 to 60 in 0.1 second. In practice, there's physical limitations that won't work. Case in point, in my shop class in high school, one of the projects was to take a Ford Pinto, a little bitty subcompact car, and put a 455 engine in the Pinto. And they did it. However, first time they popped the clutch, they twisted the frame, so it didn't quite work. Again, you've got some physical limitations on the system. As a rule of thumb, typically in control systems, we assume you can speed up the system by a factor 2, maybe 3. Beyond that, you're probably going to push the physical limits of the system. So likewise, you don't go overboard. Add a lead compensator to speed it up a little bit. But if you try to make it go too fast, it's probably not going to work. So summarizing, we've got the original gain compensation system, like we did last lecture. That would give you a error constant and a settling time and the initial input voltage at t equals 0. If I had a lead compensator canceling the wrong pole, I make the error constant worse. Cancel the correct pole, not the slowest pole, but the next slowest pole. I get better tracking and a faster system. And if I really go overboard, add 2 lead compensators, I'll have even better tracking and even faster system. But it does come at a cost. My input went from 5 to 100 to 1,700. This assumes the motor that I have is large enough that I can actually apply that much torque. And step responses. I go from a system, this is the gain compensation in red. Lead compensator is the system in blue. Again, 20% overshoot, better tracking, quicker system. 2 lead compensators, I get the system in green, even better tracking, quicker system. And finally, if I want to add 2 lead compensators, here's the op-amp circuit that does it. The trick is take your system and split it up as 2 first-order systems. I don't know the circuit for this guy, but I do know the circuit for each of these halves. So the first half is the lead compensator, second half is the lead compensator. Both of them have 4 degrees of freedom, 3 constraints, so that resistor is arbitrary. Let's make it 1K. If I pick, let's do the blue one. Pick this one, the high frequency gain is 17, so 1 meg over this resistor 17, that's 57K. The DC gain is 1.7. 1 meg over the total is 1.7, gives this as 577K. Here's 57K, this is the remainder, 520K. And the 0, 5.4, is 1 over RC. Gives C as 0.35 microfarads. Do likewise on the first half, put them together. I now have 2 lead compensators cascaded. And with that, we have lecture number 23 for ECE 461, lead compensator design.